Okay, we are continuing on here with equilibrium. Um, last time we talked about a couple of important things. The first one I think was not that maybe was Q. Q is the reaction quotient. We use Q when we're at a situation really two ways. One situation is we are not sure if we are at equilibrium. And we could calculate Q to help us decide first off that question, has the system reached equilibrium? The second thing that will also tell us is if we have not reached equilibrium, basically which way we need to go to eventually reach equilibrium. So what I mean is, do we need to make more products? Do we need to make more reactants? Remember that Q is basically calculated the identical way as the equilibrium constant, which basically means you're going to take your products and you're going to divide it by your reactants. You're going to obviously use the coefficients like we do with the equilibrium constant, the exact same thing as the exponents. Obviously, in this case, if you calculate Q and you are less than K, you are not at equilibrium. And to reach equilibrium, you need to make more products. Calculate Q and it's greater than K, you're not at equilibrium. To reach equilibrium, you need to make more reactants. And if you calculate Q and it does equal K, you are at equilibrium. So that's a very common sort of question that you're asked to answer using Q. It was just a straight sort of Q problem. I sometimes refer to it. And it basically asks those two things, are you at equilibrium? And if not, which way you need to go. In order to calculate Q, because you need products over reactants, the only way that you're able to calculate Q is a situation when you are given the concentrations or the pressures of everybody. So everybody involved, you need to have those given to you to be able to calculate Q. Otherwise, you have no way to calculate Q because you're missing some concentrations or pressures and stuff like that. In addition, typically you will have the K value given to you or available to you that you could use to compare Q to. The other situation is you might want to use Q and should use Q when you are given the concentrations of everybody in a reaction and you're doing some type of ice table calculation where you're trying to figure out the equilibrium concentrations. You should calculate Q. What it will affect is, perhaps the change part of it. So speaking of that, that was the other major thing that we did, which was calculating equilibrium concentrations. Remember that we use a ice table to do this. Ice meaning, again, initial, change, and equilibrium. Let's go down there. So how we do an ice table is we typically will just take the equation and we'll take our initial concentrations that we have. A lot of times you're not given the concentration there of the products. Doesn't really look like a zero, but you can safely assume that that's a zero. Almost looks like a circle, something there. That was supposed to be a zero. So you can assume that you have zero there to start with for our product side if you're not given anything. That also makes the change part pretty easy because you have no products, you could assume that this reaction is most likely going to favor the forward direction in this case, because frankly, you don't have any products made, so it wants to make some products. That means as time goes by here, our reactant should decrease and our product should increase. And that's going to be negatives there on our subtractions from the reactant side and positives from the product side. The important part of this, if you remember, is we also need to take into account the coefficients, because essentially what that does is take into account the mole-to-mole relationship, the proper stoichiometry when you're doing these calculations. If you ignore them, then frankly, you'll get the wrong answer because you don't really have the right stoichiometry involved. We do just kind of bring everybody down here, molarity minus initial molarity, minus X, initial molarity, minus X, and then 2X. We then go into our equilibrium constant expression with all those, and we solve for X. Now, solving for x can be done in multiple different ways mathematically. Again, probably the most complicated that we will do in here would be the quadratic. And just a reminder, that is something like ax squared plus bx plus c is equal to 0, where x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. A reminder that if you do use the quadratic, you do get 2 answers out of that. In most cases, one of the answers should not make sense. And what that means is when you go back to your equilibrium line and you put that x value into one of those, you most likely you'll end up with a negative number, which obviously you cannot have a negative concentration or pressure. So that's usually the situation that occurs. You shouldn't just disregard the values that you get because maybe they're both positive, they're both negative, or one of each. That is all the combinations that you can get, and it can work. Even with 2 negatives, sometimes it can actually work. But one of them will lead you to an answer that doesn't make sense. Any questions on any of that there? Okay, so why don't we continue on with our journey through ice tables here? And why don't you start with this one here? Take a few minutes here or some time and work this one out. We got 0.5 moles of H2, 0.5 moles of I2 placed in a 1 liter flask. What is the equilibrium concentrations of everybody if the equilibrium constant is 54.3? All right, so work on it for a bit here, then we'll go over it together, make sure everybody's on the same page here. Okay, let's take a peek here, see how we're doing here. So obviously we have some moles given to us, we have the volume given to us. We could get the concentration of each of those guys, or the molarity. We have the equilibrium constant. We're looking for our equilibrium concentration. So first thing we'll do is convert those moles into molarity. So the concentration of H2 would be 0.5 moles and divided by our liters, which happens to be 1. That makes it easy. So that's going to be 0.5 molar. We will also do the same thing for our I2. It ends up being the exact same thing. So taking our moles divided by our liters, we'll convert these guys into molarity. So we'll do our ice table. So I'm just going to flip the page here to do that. Oh, by the way, we could also write our equilibrium expression. Our K in this case would be the concentration of HI. We do need to square it because of the coefficient, divided by the concentration of H2 times the concentration of I2, and that will equal our 54.3. So obviously we might want our expression as well. All right, now we have our expression, we have their concentrations, we're ready to go into our ice table here. And let us do that. So this is going to be, I'll borrow this, why not? Initially, we had 0.5 molar, 0.5 molar. And once again, we were not given any information about HI, so it is safe to assume that it's going to be 0 here to begin with. Once again, we could also safely assume, as we've talked about, that the reaction is heading in that direction. That means that this will then be minus x, and a plus 2x, once again, for the coefficient that is there. Bringing us down here will be 0.5 minus x, 0.5 minus x, and 2x. Any questions on the ice table there? Remember that really the goal here is to solve for x, which represents the change in these tables. So we're going to put that into our expression we just wrote on the previous page, which is this guy. So putting our equilibrium guys in there gets us basically 2x squared divided by 0.5 minus x, 0.5 minus x, and once again that will equal 54.3, I believe, at this point. At this point, we want to mathematically solve it, and here it is a perfect square, so we could do a little square root action on both sides, save us the quadratic trip down quadratic lane. So we can put a big square root on both sides. When you square root the left-hand side there, that's going to give us 2x up on top. Going to give us a 0.5 minus x. And the thing that I personally forget to do a lot of times, actually square root this number. So that's going to be 7.36885 at this point. Any questions on that? Now you could, if you wanted to, kind of factor it out and do all that kind of thing, but you know, why do the extra work if you don't necessarily need to in this case and maybe have something go wrong? We want to solve this. So again, mathematically to solve this, we got to take what's on the bottom there on the left and multiply it over to the other side. When we do that, that's going to give us 2x is equal to 3.6844 minus 7.36885x. We're then going to combine our x's. So we're going to add this guy to the other side. And when we do that, we end up with 9.36885x equals 3.6844. At this point, we're good to divide both sides. So we're going to bring this back that way and divide. When we do, we end up with an x value of 0.393 in this case. Questions on any of that math there? All right, so as we talked about, that is not necessarily the answer. That is the change or the x value. And once again, that x value that we just got there, this x value is every single x value that you basically see in that table. So we'll use that x value to solve, and that will give us that the H2 concentration would equal 0.5 minus x. And that will give us 0.107. And we do need a concentration unit there, molarity. I2 will be exactly the same. So it'll be 0.5 minus 0.393. I'll just arrow it up there. We'll get the same one for both of those guys. And then since I ran a room, I'll go top left here for our HI. That is equal to 2 times x. And for our HI, that would get us 0.786 molar here for equilibrium. Any questions on any of those things there, parts of the calculation? Once again, because it's math, we could check it. And if we take our equilibrium concentrations we just calculated and put them back into our expression, 0.786 squared divided by 0.107 divided by 0.107 gives us approximately a K value about 53.96 or about 54. So that's pretty close to what we had. And that's, again, a good way to, just double check nothing went wrong along the way. Any questions on that there? We also have a relatively large value of K, and we do see a little bit more of the concentration products there at equilibrium. So kind of makes sense as well. Any questions on that one? All right, fun with math. Here we go. Let's try another one here. All right, we're going to use basically the same reaction, the same K value, but in this case, we are dumping in there 0.00623 molar H2, 0.00414 molar I2. And in this case, we got a little bit of HI happening as well, 0.0224. Okay, let's take a look, see how we're progressing on this one here. A little bit of math going on, I suppose. All right. So in this particular case here, we're given the concentrations of everybody to start with. So we got a little bit of our H2 or I2. We got some of our HI happening at this point. This is technically, we have concentrations for everybody. This would be another time that you should probably calculate Q here, just to make sure you understand which way this one is proceeding. If we did calculate Q, Once again, it would be calculated the exact same way as we would do K. It would be the concentrations of HI squared divided by H2 and I2. Here we would put in our values. So that would give us Q is equal to HI, which was 0.0224. We'll do a little squaring. Divided by our HI, which was 0.00623. And our 0.00414 for our I2. Putting those values in to a calculator. Going to get us a 19, we'll call it 19.5 as our Q value here. In this case, we are obviously given the K value, that is 54.3. In this case, Q is less than K, right? That tells us we are not at equilibrium, which we probably could have guessed because it wouldn't have been much of a problem at that point, right? So it does tell us which way we need to go to reach equilibrium. We need to go opposite of where that's pointing. So we need to go to the product side. So now we can feel very safe that we are having the reaction go in the forward direction and that our negatives are on the right side and our positives are on the right side. Again, this would obviously affect the change part of your ice table, right? If you had the opposite occur. So here we can feel good. If you blew through it, you'd probably be okay in most cases, not all cases, but in most cases, if you blew through it, didn't do the Q part, you'd probably still be okay. And again, a lot of cases, not 100% of the time. All right, now that we have everything sort of set up here, we're going to go into our ice table and do our equilibrium calculation here. So we'll rewrite our equation, start with that. So we have H2, I believe, plus I2 going to 2HI. And we have an initial of everybody in here. So our HI there was 0.00623. Make sure I get in the right spot there. 0.00623. Our I2 0.00414. And again, here we're not going to put this as 0 because we do have an initial concentration here for our HI, which would obviously be what we got there, 0.0224. Change part here, we're going to go minus x, and this is plus 2x here. Again, remember that it is plus on this side. Sometimes people are used to, like, I have a number, then it's got to be minus x or stuff like that. Carrying this down, going to get us 0.00623 minus x, 0.00414 minus x, 0.0224 plus a 2x. Any questions on the table here? All right, so obviously this is going to go into our equilibrium expression, which is obviously the same expression as we just used for Q. So K here would be the concentration of HI squared divided by our H2 and our I2. And we'll put our numbers in. That will give us 0.0224 plus 2x squared divided by 0.00623 minus x, 0.00414 minus x, and that's all going to equal 54.3. All right, at this point, we got a little bit of math to do here. This is not a perfect square, so you can't square root both sides. You got to do some factoring, whatever they call that now, distribution, all that good stuff of really the top and the bottom, right, to start with. So what I'm going to do is just kind of do them separately here. So make sure we end up with the same thing. So I'll do a dash line here. We'll go here. I'm going to start with the, I think I'll start with the top part here. And by top, obviously, I mean that right there. So we're going to take 0.0224 plus 2x and times it by itself there. And obviously, right, in and out, yes, on both sides. When you do that guy, you do end up, I believe, with 0.000502 plus 0.0896x plus 4x squared. And that's obviously 0.0224 times 2 twice. So before you kind of put it together, you end up with, for this guy, 0.00502 plus 0.0448x plus 0.0448x plus 4x squared. Combining these two get us to that guy basically for the top. Yeah. Any questions on that there? Okay, I'm gonna kind of do the same thing for the bottom, and then I'm gonna kind of put everything back together. I'm just gonna flip the page there to do the bottom part. So we'll do the bottom factoring out there just to make sure everybody's good. So we'll do the bottom here next. And if we do that, taking our two that we got 0.00623 minus x, 0.00414 minus x. Once again, we're going to go in and out on both of those. So if we do that, we end up with here 2.58 times 10 to the minus 5 minus 0.00623x minus 0.00414x plus x squared. Once again, doing a little combo of those two guys there and kind of flipping it back around the other way will get us basically like an x squared plus, I'm sorry, x squared minus 0.0104x plus 2.58 times 10 to the minus 5 there. Any questions on that factoring there? All right. All right, so we got our top guy that's been factored. We got our bottom guy that's been factored. So let's put them back together into our expression in the right locations. So once again, that was the bottom part there that we were doing. Okay, so putting it back into our K expression, our top one on the top there and our bottom one on the bottom. So our top one there was 4x squared plus 0.0896x plus 0.000502 divided by our bottom, which ended up being x squared. Keep on doing plus, which would not be good. Minus minus here 0.0104x, and that's going to be plus 2.58 times 10 to the minus 5, and that will once again equal our 54.3. All right, so I just took my two parts, put it back together. Now I'm still got a little bit more math to do. To solve this correctly, we got to take what's on the bottom, right, and multiply it over to the other side. That will leave the top part alone and nothing happens to the top part. So the top part still stays as 4x squared plus 0.0896x plus 0.000502. Now multiplying everything on the bottom to the other side is going to get me 54.3x squared minus 0.565x plus 1.4 times 10 to the minus 3. Any questions on that there? Lastly here, I wouldn't say lastly, but closely here, we're going to bring everybody to the same side, right? So in this case, I'm going to keep that first number positive. So for my example here, I'm going to bring everybody to this side. And by that, I'm not dividing or anything like that. I'm adding and subtracting right to the other side. And when I do that, it gives us our cleaned up for equation here of 50.3 x squared minus 0.655x plus 8.98 times 10 to the minus 4 is equal to 0. Give or take a little with some rounding, depending on where you rounded. At that point, that is our quadratic, which gives us our A, B, and C value here. Any questions on that there? All right, now we're ready to go into our quadratic with our A, B, and C values. So I'm gonna flip the page there and do that. Everybody good? Yeah. All right, so our x is gonna equal minus b plus or minus the square root, b squared minus 4ac divided by 2a. And once again, I'll write our equation next to it, 50.3x squared minus 0.655x plus 8.98 times 10 to the minus 4 in this case. It's going to equal 0. All right. Yeah. You might have got a slightly different number depending if you rounded or didn't round. So I did a little bit of rounding there. But if you got a number, hopefully close to that, I would hope, yeah. So 0.652691. Did you get a completely different number? Like completely different than that? Yeah. Okay. Okay. All right. I think that should be right. So just to make sure, that would have came from, we're bringing 0.565, and then we're going to subtract 0.0896. Right. Is that right? So let me just double check here. I didn't miscopy something here. Then going that way, and we're going to subtract that. So that's negative. So we're going to take 0.565 basically and add it to 0.0896. So you should get something like 0.6545, something like that. Yeah. Because this is negative, so that should become negative. So basically we're adding those two numbers together when we take it to the other side. Yeah. Other questions? Okay, so we'll put our numbers in. This is going to give us x is equal to minus b, which would be 0.655 plus or minus. When you put everything in the square root, before you take the square root, you got something like 0.2483. Once you take the square root, you end up with 0.498, give or take, divided by 2 times 50.3, which gives us 100.6. In this case, we then get an x value going the positive way of 0.0115, and an x value going the negative way of 0.00156. Yeah. Any questions on that so far? Once again, here, I'm not going to rewrite the entire ice table, but I'm just going to bring the equilibrium line down. So we had our H2 plus our I2 goes to our 2HI, and our equilibrium line was 0.00623 minus X, 0.00414 minus X, and 0.0224 plus 2X. So in this particular case, if we look at it, we can see that this number is actually too big, right? because if we put it back in, we will get a negative value. So it actually is the number there to the right. And using that number to get our equilibrium concentrations, 0.00623 minus 0.00156 for our H2 gets us something like 0.00467 molar. For our I2, 0.00414 minus 0.00156 gets us for the I2 0.00258. And lastly, for our HI, it's important here not to forget the first part, 0.0224 plus 2 times 0.00156. And that gets us 0.0255 molar in this case. And we could see if we did not too bad here to make sure. We take our 0.0255 and square it, and then divide it by 0.00467 and divide it by 0.00258. Gets us about 54, which is pretty good as to where we started in terms of that. Any questions along the way? Yes. Maybe, yeah. You never know what numbers I make up as we go through it, you know. So you should be able to do this, yes. So it is something that you need to do. You do need to show the work, even if your calculator could do the quadratic formula for you. You got to show some work, yeah. Can't just pop it in there and hope for the best, yes. Because I've seen people pop it in and pop it in wrong to their calculator. So you still got to show the work, yeah. Even if your calculator could do a little quadratic function for you. Yeah. Any questions on that there? I would say if you could do this one, you should be able to do anyone, I would hope, yeah. But this does bring up a couple of really important parts. Obviously, you do want to be careful as you're moving around with numbers. I mess up sometimes as well. So you do want to be careful as you move kind of through it. If you do it in parts like I did, make sure you kind of keep it organized so you know which part you're doing. So when you put it back together, everything goes back together correctly. You're not just looking at your paper of like, what is that equation for, or which part of it is it? And then I would also obviously do a little check of this here at an end of a problem like this, just to make sure. No guarantee, but at least you have a fairly good shot at it. Any questions on any of that there? Okay. All right, one more here. The KP in this case is 4.31 times 10 to the minus 4. Calculate the pressures of everybody at equilibrium. If we started with 0.862 atmospheres of N2 and 0.373 atmospheres of H2 in a constant volume vessel. So this is KP. These are pressures. Frankly, works the same way. Got to roll an ice table, works exactly the same. This is what we talked about as well earlier, that if you are doing an ice table like what we're doing here, you need to make sure these things are in atmospheres, which they are at this point. So this is where that what I was talking about earlier, that you got to make sure these things are in atmospheres when you go into the ice table. Okay, go for it. Give us a try for a bit here. We'll go over it. Okay, let's take a look here and see how we're progressing. So again, as I mentioned, if you have a KP value and you have some pressures, it really doesn't matter. It works the same way as concentrations. Again, the one key thing you have to watch out for, as I mentioned a couple of times, is the units of the pressures. Even as I mentioned earlier, in a problem where they maybe give you the pressure in, say, torr or something like that, and they actually want you maybe to give the answer in torr. Again, some people think, well, then I could just kind of leave it in torr, but you cannot. So you do have to kind of convert it to atmospheres, go into the ice table, do the ice table calculation, and then convert it at the back end of the calculation back to the same unit. So always make sure it's in atmospheres when it goes into an ice table, even if it gives it to you in one unit and wants the same unit and it's not atmospheres, you got to do that. So that's how we'll approach this here. We got our equation, so let's get a fresh move on that. And we're going to put our initial pressures in this case and our Initial pressure there, I think of N2 is 0.862. H2 is 0.373. And once again, we were not given anything for our product side. We will do our change, which will be minus x minus 3x, again, because of the coefficient, obviously, that's there. And on this side, this will be plus 2x, bringing us down to 0.862 minus x, 0.373 minus 3x, and 2x in this case. Any questions on the ICE table here? This is going to go into our equilibrium expression, which I guess we should write would be good. So our Kp in this case would be the partial pressure squared of NH3 divided by the partial pressure of N2 times the partial pressure cubed of H2. And that obviously would equal what they gave us, which was 4.31 times 10 to the minus 4. At this point, just like normal here, we're going to put our equilibrium line into the expression. And at that point, that would get us a 2x squared divided by 0.862 minus x, 0.373 minus 3x. We do need to cube it as well. And that will equal 4.31 times 10 to the minus 4. At this point, we should probably go to another problem. Is it a good idea? I think. All right, so we do need to solve it. We shouldn't run away from it too fastly. We could do it math-wise and have a lot of math fun, but nobody wants to have math fun, right? So we do want to maybe look at an alternative way that maybe we could solve this without, ripping our hair out of doing the math. So in this particular case, if I look at my equilibrium constant value here, is this value a large value or a small value? It is a small value, this value here. That means when I reach equilibrium, would I mainly have reactants or products present? I would mainly have reactants present. And if when I reach equilibrium, I mainly have reactants present, would that mean the change part here should be a big change or a small change? Should be a small change, right? If you mainly have reactants, that means you didn't use a lot of reactants to go to product side, right? So it should be a very small sort of change. So in a situation like this, when you have a small value of K, you can make an assumption and you could assume that X is equal to 0. Now, clearly you cannot take out all the X's because then you got nothing to solve for. So that's not good. So what we're talking about in general in this case is you're going to get rid of all the X's that you're subtracting from a number, or maybe you're adding to a number, any of those that you're subtracting and adding. This one you cannot get rid of because frankly, you started at 0. So anything that you get is more than you started with. So it's a big change that occurs. So you can't get rid of that one. But it's really these X's here that we could get rid of. So if we get rid of the X's there, this now simplifies this down to 2x squared divided by 0.862 times 0.373 cubed is equal to 4.31 times 10 to the minus 4. I don't know about you, but I'd much rather solve that one than the one above it, right? So if we're going to solve the one below, you do obviously, as you see there, still need to cube the number and all that, so you don't want to mess that up. We're going to take care of the bottom here basically and then multiply it to the other side. Yeah, so we're going to multiply those guys and then take it to the other side. And if we do that, 0.373 cubed times 0.862 gets you something like 0.00, if you kind of come out this way, 0.00447. We're then going to multiply that to the other side, 4.31 exponent minus 4. going to give us basically 4x squared is equal to 0.00001928. We're going to divide the 4 to the other side and also take the square root as well. So we're going to divide by 4, take a little square root action, and that is going to get us an x value of, we'll call it 2.20 times 10 to the 2 minus 3 in this case. Any questions on that there? So once again, on that last move, I divided by 4 and also took the square root. Yes. Yeah. I got rid of the x because frankly, I didn't want to do the math. No, I got rid of the x because in this particular case, the equilibrium constant value is a small value. And that means that when you reach equilibrium, you will mainly have reactants present. But really what that means in that case is not a lot of reactants are going to the product side. That means that the change that's going to occur from reactants to products will be relatively small. So small as negligible. We basically assume that it's going to be 0 in this case. Yeah. Did I just not write it? I might have had it with me to make sure. You might be right. I might have just lost a 0 there when I wrote it. Let me just make sure here. I think I put an extra 0 is what you're saying, right? So it should be point. Yeah, I did. Sorry about that. Good news is I continued on with the number of my calculator, so I think the other number is good, right? So that is, should be 0.0447. Thank you. And I believe the other number should be good, right? Excuse me. Okay. So yeah. Say again. You can use this assumption if the K value is small. I'll put it this way. You could try the assumption if the K value is small. And we're going to talk about how you know it's good or not. And right now we'll talk about it actually at this point. So when you do this assumption, you do need to actually check your assumption to make sure that it is okay to use. Now, there's a couple of different ways that you can check your assumption. We're going to use what they used to call years ago. They might still call it that, the 5% rule. And the 5% rule is this. You basically take the X value that you just got. So in our case, the X value we just got was X was equal to 2.2 times 10 to the minus 3. So you take the X value and then you basically go back and divide it by what you were going to subtract it from. And you times it by 100. And if it's less than 5%, you're good. If it's more than 5%, not so good. So we'll show you how that works. So we're going to take our X value we got, 2.2 times 10 to the minus 3. We're going to divide it by what we were going to subtract it from. So 0.862 in one case. And times it by 100. So 862 times 100%. So 2.2 to the minus 3 divided by 0.862 times 100 gets us 0.255%. That is less than 5%. That means that's a big smile. You can use it. It's all good. If you get over 100%, yeah, you get over 100%, definitely don't use it. But if you get over 5%, that means you need to go back and solve it some other way. The some other way in our case would be you probably have to throw it into a quadratic formula and solve it that way. Can you check them both? You can, and you probably should. But even, excuse me, even if you check them both, in my experience, if one of them is good, usually the other one is good as well. So for example, if we did the other one there, we would actually take 3 times the X value. So we would take 3 times 2.2 times 10 to the minus 3 and divide it by 0.3 0.73 times 100%. And that gets us like 1.77%. So it is still good. It's less than 5%. So you can do either one. Like I said, in my experience, probably if you check the first one, it's good. You're probably good. You don't need to check every single one. There might be a rare occasion where it won't work, but usually you should be good, I think, if you just check one. Any questions on that there? And again, once again, if it was over 5, you would have to go back and kind of solve it some other way through the quadratic. All right, now that we checked that it's all good, we actually should solve the deal here. So that means that our pressure of N2 would be 0.862 minus X. And that would be 0.862 minus 2.2 to the minus 3. Gets us a 0.8, we'll call it 60 atmospheres. Needs a unit since it's a pressure. For our H2, it would be 0.373 minus 3 times 2.2 times 10 to the minus 3. And that would get us 0.373 minus 3 times 2.2 to the minus 3. Looks like 0.366 atmospheres. And lastly, from our ice table there, NH3 is just 2x. Yeah, so that would be 2 times 2.2 times 10 to the minus 3. Going to give us 0.0044 atmospheres in this particular case. Any questions on that calculation? Once again, we could check it. We take that number, square it, divide it by 0.860, divided by what we got there, 0.366 cubed, I believe. This is something like 4 point something times 10 to the minus 4, so we should be good, I think, in that case. Any questions on any of that there? Now, the question is, why did I not use the assumption on our previous problems? Could I have used the assumption on our previous problems? The answer is our previous problems, if you look at the K value, the very first one we did the other day was like 7, I think. The last ones that we did were 54.3. Those are large values of K, which means you cannot use the assumption in those cases because the change should be relatively significant because you should have products at the end. So you cannot use the assumption again if the K value is large. If the K value is small, you could try it. It won't always work. So you should always check it. As we get into future chapters, there will be places where it will not work. You need to check it to make sure. And again, you got to go back and solve it some other way. So again, for us, that would be our quadratic. So we now seen in our day of ice tables, we have now seen 3 different ways that you could solve an ice table problem. You could have a nice perfect square. You can use your favorite quadratic and do some factor labeling or whatever that is called. And you can make an assumption. So those are 3 ways that we will solve these problems. As I mentioned, I think the other day, the one way that we will never do in this class is successive approximation. But again, you may see that in your book and stuff like that. So some books will, or some problems can be solved by successive approximation. As I mentioned before, successive approximation is essentially where you go, I know it's like 0.862 minus X, so it's got to be less than 0.862. So you sort of pick a number, solve for X, and then you keep kind of doing that until the number you pick and the number you get out is the same number, then you solved it. And it can be a lot of times doing that if you're not really good at it. But you should note that that is a way some books and stuff solve problems. So if you see it somewhere, you know, they might be doing something like that. But those are the 3 ways that we will solve ice table problems. Any questions on that there? Okay, we were laid up there for today.